These are your instructions. As usual, just follow the PowerPoint. Make sure the sound is turned up on your device so you can hear the narration. Your instructions are in yellow boxes on the relevant slides. Remember, if a slide asks for homework, don't forget to send it in via Show My Homework. And if a slide asks for Educate to be completed, don't forget to do it by the date given on the slide. These are our lesson objectives for this lesson: to understand what is meant by a moment, to know and apply the equation to calculate moments, and to explain how and when an object is balanced or in equilibrium. Have a look at this picture. It's common sense, but there are two things we can do to get the seesaw to balance. Write both of them down if you can. The 2 points you could have made are: one, you could add some more mass on the left-hand side. That would increase the force on the left-hand side. That would level the seesaw. But also on the right-hand side, if you move the single stone closer towards the middle, that lessens the effect it has, and that would also balance it. This idea of a turning effect caused by a combination of the force and the distance from the pivot is what moments is all about. There is some vocabulary which is useful for this lesson. Firstly, a pivot or a fulcrum is the point about which a system turns. For instance, the center of a seesaw. When we say a system is in equilibrium, we mean it's in a state of balance. Nothing is going to change in that system unless you make a change. And finally, we need to remember what we mean by clockwise and anti-clockwise. This is a way for us to say which direction forces are acting in, and it compares it to the hands on a traditional clock. So clockwise is as a clock would go, and anti-clockwise is the opposite direction, sometimes called counterclockwise. A good skill to have is to be able to simplify problems. Have a look at the picture on the left-hand side of this slide, and then simplify it and draw the simple version in your books. This system consists of a weight and a man's arm. Draw a simplified version of it. Bear in mind that this time both forces are acting to the left of the pivot. Here are some more examples of systems that you can draw simplified diagrams of. In each case, make sure you label the forces and make sure they are in the correct direction, and also label the fulcrum or pivot. The size of a moment or of a turning force depends on two things. It depends on the size of the force, measured in newtons, and how far from the pivot the force acts. Now you have to be careful measuring this distance because it's the perpendicular distance at right angles. The moment is calculated by multiplying the force times the distance, often abbreviated to m equals fd. Be careful how you write your equations. Make sure you have the capitals in the right places. Moment doesn't have its own unit. You just multiply the force and the distance units, giving you the Newton meter. This slide shows that equation being used. You have the same situation in both pictures. What is different is the size of the force and how far from the pivot that force is acting. So in the first picture, the force is 10 newtons and is acting 15 centimeters or 0.15 meters from the pivot. If you use your equation, moment equals force times distance, this gives you 2.25 Newton meters anti-clockwise. If you look, the force is acting this way, so it's turning this way. That is anti-clockwise. In the second picture, the force is 20 newtons acting here, and the perpendicular distance is 20 centimeters or 0.2 meters. Again, if we apply our equation, moment equals force times distance gives us 20 times 0.2 is 4 Newton meters. So using the equation, we can say that applying this force at this distance has a greater moment or turning effect than using this force at this distance. Remember, if you want a larger moment, You can either increase the force or you can increase the distance from the pivot. A special situation occurs when the anti-clockwise moments are equal to the clockwise moment. In this case, we say the system is at balance or it is in equilibrium. This is a simplified exam question. All the forces and dimensions are given. Your job is to prove that the system is in equilibrium. So you want to prove that the clockwise moment is equal to the anti-clockwise moment. Pause the recording here and try it. So what we have to do here is decide what's happening to the left and to the right of the pivot, i.e. in a clockwise and anti-clockwise direction. This is often referred to as taking moments about the pivot. So, taking moments about the pivot, clockwise you have a force of 75 newtons acting at 0.04 meters. That gives you a clockwise moment of 3 Newton meters. Anti-clockwise, travelling this way, you have a force of 10 newtons at a distance of 0.3 meters. And if you calculate that, that gives you again 3 Newton meters. This means if the clockwise and anti-clockwise moments are the same, the system is in equilibrium, it is at balance. You can also do this process in reverse. If you start off knowing that a system is in equilibrium or is at balance, then you know that the clockwise moments are going to equal the anti-clockwise moments. So in this case, you know that this force times this distance is going to equal this force times this distance. This means that if you know 3 of these quantities, you can work out the 4th one. So in this case, we know that 200 times 10 meters is going to equal the mystery force times 5 meters. If you do the calculation, to make it balance, the mystery force is 400 newtons. Here are some examples for you to work out. In each case, do the calculations and decide whether the seesaw will be balanced or unbalanced. Green pen your answers using this slide. Here are some more questions for you. This time, see if you can work out the missing distance or the missing mass. All of these systems are at balance. This is a slightly trickier question. A uniform 6-meter long steel girder weighing 1,000 newtons rests horizontally on a pole 1 meter from one end. What is the tension in a supporting cable attached vertically to the other end? The difficult bit about this question is actually picturing it. So this is the girder, 6 meters long, and it's resting on a pole. So this pole is the pivot and it's going away from you into the page or into your screen. Then here you have the weight acting in this direction, and it would pull the beam, the girder, that way, but there is a cable here holding it up. Now it says in the question that it's horizontal. So what that means is, you know, because it's horizontal, the system is at equilibrium. And if a system is at equilibrium, you know that the clockwise moments have to equal the anti-clockwise moments. Now, having said all of that, try the question. Green pen your answer using this slide. Answer questions 1 to 10 on the attached PDF. Send photos of your notes and answers 1 to 10 from the worksheet to Mr. Rahman by Monday the 11th of May. Thank you.